Hello everyone, today I want to show you the simulation case of the motion of a top. And as we can see, in the left viewport, we can see a spinning top. And on the right viewport, we can see a curve, and it is the position of the bottom point of the top. And here is the x coordinate, and here is the y coordinate of the bottom point. So let me show you how to create this model and do the analysis. First, we can see there are 4 parts in this model, but actually we just have one part, and the other is reference point. Here is a new part I will create as the top, and this is the top point of the top, and here is the ground reference point, and here is the top. It is an analytical, a rigid body, and here is a coordinate and a represent point. This point is the coordinate is the bottom point of the top. So how can we create this top? It is simple revoluted rigid body. Let me show you how to create it. Of course, we don't need the lens, so we delete it or trim it. So here is the revoluted analytical rigid body. Here we have O1, and there is a coordinate system. The coordinate system is a little deviated from the global coordinate system in the y-axis. So because there is no deformable part, so we don't need any material or sections. Then we can enter the module, the assembly module. Here we adjustment the position of the top and make it in the correct position. Here it is. If we make a more one, we can know how to rotate it to the correct position. Here, it rotates with the x-axis with 110 degrees. I have measured that. So then in the step module, we create a dynamic implicit step. Dynamic implicit step and make time 3 seconds and the increment size 0.01 and 0.01. And here we need to 3000 increments and click OK. So here is the step we created. Here we used the fixed increment step. So after we have created the step, we need to create the output. But before that, we need to create the connector and some set for output. So we get into the interaction module. Here we need to create two connector property. The first is beam, but we don't need any behavior settings. So let's save it and give it the name and the Ola connect section. Ola, and it is in the basic component and rotational type. Here is the Ola connector. Here is a diagram for interpretation. It is a rotation connector type, and it can output the three different angle of rotation relative to the coordinate systems. So after we create the connect property, we need to create the wear lengths. We need to create two wear lengths. The first is the bottom point to the apex, and here the set, and this is the feature. The beam is wear length for the beam connector, and the 2 points is this one and the vertex apex. So we need to create like this. Geometry type polyline, and we click the add and select the first point and the second point, because there are 2 points in the same coordinates, so we can select the right one. Here is the ground, and it is used for the Ola connect. So we need to click next, and here we can see the vertex and click OK. So this is how we create the wear length. And the second wear length we need to create is for the Ola connector, and it is between the vertex and the ground point. So we need to select this. We need to select the correct point. So the first point is vertex, and the second point is ground, and click done. So after we create these two wear lengths, as well as the set, and its default is wear set, and we rename it as beam and Ola. So then we need to assign the connector property to the wear length. So we can this, and the set is in the and it's here, and we have named it as beam and aura. So we need to select beam, and because we have created it, so set beam. Here it helps to select the beam connector, and we don't need orientation, so click OK. Similarly, we need to assign the OLA connector to the wire set OLA and get it the OLA. Here we need to specify the system coordinate system. Here we select the datum system. It is the same as the default global coordinate system. And for the second orientation, we need to select the top body axis. So this is the OLA connector, and it describes the rotation of one coordinate system about the other coordinate system. So when click OK and created the beam connector and OLA connector. Then we return to step module and create the history output. And here is for the OLA connector. For this connector, we choose set, and here we select OLA. This is the wire set. So in the variable to output, we choose the connector relative position and relative displacement and rotation. This is the OLA connector. And the second is the bottom point apex. Similarly, we choose the set, and here is the apex, this point. And for apex, we need to output the current nodal coordinates, so we can obtain the point position in the xy plane. For other is the translation and rotation, because this point is rotating and spinning. So this is the history output for connector and the point. Then we need to set up the boundary condition and initial velocity and the force. First, we create the boundary condition. Here is the ground point is axistal, it's fixed, and for the top point, it is pinned, so it cannot translate in any direction, but it can rotate about any axis. So this is the boundary condition. Then we need to create the initial angular velocity. So for the spinning motion, we need to set the initial velocity and select the vortex. This is the vortex at the top position. Okay, let me show you. Here, mechanical velocity and vortex. And we just need the rotational. So here is the rotational angular velocity, and then we need to 2 points to determine the axis. The points we can see here, 0, 0, 0, and 0.5, negative 17.101, and 46.984. We need to change these parameters to what we want, so it can have different results. Then the top is subjected to a force and in the z direction. So and it represents gravity force. So here is negative 20 newtons in the negative z direction. Because it has an initial angular velocity, then it's subjected to a force. So this is a top after a whipping, so it can keep rotating and spinning. Then we get into the mesh module. Here we don't have create any mesh because they're all a rigid part. So we just create the job and submit it. After about 10 minutes or 20 minutes, this job will complete it, and then we can see the result. This is the rotation of the top, and it is spinning. See? And also we can see there are many history output here. We can see every curve in the output. This is the relative displacement and rotation. So here is the coordinates of the bottom point. We can see here. This is the x coordinate, and here is the y coordinate and z coordinate. This is x and y. So this is the apex displacement. So we can see position or displacement of every node here. such as we want to see the relative displacement of x of the apex. We can plot it here. Just as the output, history output. And for this curve, how can we get it? Because this is the bottom point of the coordinate. So here we have output the coordinate of the point, and this is for the x coordinate and the y coordinate. We create the plot at the same time, and then we need a operation of combine here, and the first axis is x and second is y. Then plot it. Here we create this curve. It is absolutely the same here. Okay, this is the today's tutorial. So if you are interested in Abaqus CAE simulation, please subscribe my channel and contact me by email. Thank you for watching.